Welcome to another podcast episode showcasing innovative solutions for nature conservation. How can we protect our Earth and nature in times of increasing natural disasters? This week, we will shed light on the role of science in the field of nature conservation. To do so, we will get to know the Destination Earth initiative that is aimed to help the European Union become climate neutral by 2050. But before we start, we are very excited to welcome our guest today, a computer scientist from ETH Zurich, one of the world's leading universities in science and technology. Thank you so much for joining us, Torsten. Would you like to briefly introduce yourself to our listeners?
Yes, thank you. So my name is Torsten Hoefler. I'm a professor of computer science at ETH Zurich in the computer science department. And I'm mostly working on high-performance parallel computing, which basically means that we're building the largest computers of the planet, and we are trying to solve relevant problems on these computers, typically problems of national or international importance that are advancing you could say, advancing societies or advancing humanity.
And one of these projects of international importance is the Destination Earth initiative. What is the idea behind this project?
So the idea here, at least the part that I'm looking at specifically, is to create a digital twin of our planet Earth, where we can simulate pretty much in real time what is happening with Earth, like how is Earth reacting to what we do. And really trying to understand and trying to forecast, and in the near term as well as in the long term, what is happening.
Wow, so with the digital twin of Earth, it should become possible to simulate environmental issues before they really happen. How can this help policymakers to protect our nature and climate?
And just to give you an example, a couple of years ago I was an advisor to the late Paul Allen, who was one of the co-founders of Microsoft, a multi-billionaire. And so at the time he was planning to spend $500 million on improving the quality of climate simulation codes to really understand the impacts that humanity and policymaking has on the Earth. Because what he found when he looked at this in detail, he found that the predictions we have today are actually not very accurate. I'm actually hoping that these digital twins will have very, very tangible predictive outcomes for policymakers. So for example, how do we want to react to natural disasters? Like have certain policies in place to protect ourselves from this constant damage of these natural events. And this is what a digital twin could actually really help to just simulate the statistical distribution. How likely is it that there will be a hailstorm in a certain region in 5 years? Is that likelihood going up from today? Is it going down? Because these things are shifting.
Mm-hmm. Well, that sounds really promising, but how does something like this work? Could you try to explain the functioning of the digital twin to us as non-computer science experts?
So that is a bit more complicated, yes. So how does it actually work? We have been doing weather and climate prediction, mostly weather prediction, since a very long time, so the beginning of the 20th century. So how do we do this? Well, this is even more complex to explain, but at the bottom of it, there are two aspects to it to predict the weather of the future. First of all, we need to understand the physical equations that govern the behavior of nature. The second aspect, once we have the governing equations, is actually the current state of the system. What we do is we take the state of the system and then we apply the governing equations to predict the future. And so what I'm doing concretely is then helping to design supercomputer systems, so supercomputing machines, that are executing this problem, this computation, this extremely challenging computation, as efficiently as possible.
Well, thank you for giving us this general picture of how this can be done, although we must say it is quite difficult to fully grasp the idea behind it all. So, for example, what do you mean when you say you're trying to design the supercomputer machines as efficiently as possible?
Well, there are multiple aspects to efficiency. So there's one financial aspect. Of course, we need to be able to pay for it. But in my view, even more important is the energy aspects. So how much energy are we spending on performing that calculation? Some of these calculations require gigawatt hours of energy to actually execute. This is not happening because, after all, we want to predict the climate, we want to positively impact the climate. So it would be very bad if our CO2 emissions of that calculation would be larger than the positive impact of that calculation.
Yes, that makes a lot of sense, and it truly is incredible. And who is involved in this process of making all of this possible?
So who's involved? I mean, a lot of people. The most important people are the climate scientists, the domain scientists, the people that actually understands what's going on in the climate sciences. So they understand the data sources, they have the models, they do understand how clouds form, they understand how tornadoes form. So these are at the very top. Those people typically rely on computational mathematicians to help them to formulate their problem as a set of equations that solve the problem for them in order to predict the future. So then these computational mathematicians, they usually rely on computational scientists that help them to actually implement these equations on a computational system. And then these computational scientists, they actually rely on computer scientists like me to build programming languages and machines that they can express their problem on, that is running on a real computer. So you can see there's already four types of different roles of people involved. And this is not just, these are just roles. So in each of those roles, there are dozens, if not hundreds of different individuals helping with the process to express this all. And so it's quite interesting to look at this cross-cutting area.
Mm-hmm. And is it challenging to cooperate across all of these different roles and positions?
It's challenging, but at the same time incredibly satisfying. So I have to say I'm working with the climate scientists here at ETH, and they're incredible people. And I've never learned so much about climate and how clouds form and all of these very interesting things that you're not exposed to. Then there are these applied mathematicians, and I learned a whole lot about how you would actually phrase these problems, what kind of computations you would get to. And so I incredibly enjoy working with them. There's some problems sometimes. So we have some communication issues quite often. However, it's incredibly rewarding to exchange across these like it used to be boundaries, but now it's not boundaries anymore because we are integrated in this computational project that I really immensely enjoy being part of.
That's really nice to hear, and it also gives hope that an interdisciplinary initiative like this one really is possible. So if the collaboration continues to work so well, how much time do you think it will take for the digital twin to be created?
That's an interesting question. So if you wanted a real-time digital twin at 1 kilometer resolution, I think that could take 5 to 10 years. Because those computers that we would need to build in order to stem this calculation, they're not existing today. And they will not exist in the very near future. However, there are potentially groundbreaking developments that could lead to a significant reduction in computation time. So for example, what my team in collaboration with others is working on is trying to replace parts of the simulation with an artificial intelligence system. So I could see that there is, in addition to the artificial intelligence joker that we may have, that there may be another hardware joker moving to even more specialized architecture for climate and weather predictions, which is what we are in fact also researching in our lab, trying to understand how to build the best possible machine specifically for these simulations.
And there has, however, now been a development that could really disrupt this whole development process. And that is that the European Commission has recently decided to exclude Swiss scientists from the Destination Earth initiative. What does this mean for you and for ETH Zurich?
Well, this was a political decision. It was way above my head, obviously. I don't fully understand what this really means yet, but the question is, can we still participate in as partners in these projects? So this is still in the air, up for negotiation. That just happened recently. We have to look positively into the future, and I think there is a lot of opportunity because we have the technology to move this forward. And I would also say that there's actually a big loss for the European Union to lose this partnership with Switzerland, because Switzerland has traditionally been leading in high-performance computing among others in the European Union. So which means we would be an extremely strong partner for these. So we will see what happens. I personally hope that our partners and my friends are still interested in this collaboration. But yeah, I think we will be strong in any case.
Mm-hmm. Well, we will definitely be curious to see what happens, and we'll hope for the best until then. And speaking about hope, what are you hoping for from this project?
So from this project, I'm really hoping that we manage to build this digital twin, to improve the climate forecasting capabilities of not just Europe, but really humanity. And this is an international effort. So what I'm hoping is that with these advanced computational technologies that we are going to invent and we are going to implement and make useful for these climate scientists, we will actually really understand what the impact of our current behavior is on the Earth, and we will be able to steer it and run scenarios.
Well, thank you so much, Torsten, for taking the time and shedding light on the role of science in digital innovation. It's really fascinating what you and your team are working on, and we wish you all the best for creating the digital twin of Earth. And as a final question to you, we would like to ask you whether you have a message for potential future policymakers.
Yeah, my message would be that we should really base our policies on scientific data. We should make data-driven decisions, but we should be extremely careful about the quality of this data. And that's, of course, on both sides. So my community would need to help to communicate it, but policymakers also would need to listen. At the end, I really want policymakers, future policymakers, to work with scientists based on scientific data and also support them to get much better data that gives deeper insights and more accurate predictions.